Well, so far, we understand this by the geometrical meaning. But how about I give you a matrix like that? I cannot tell you what exactly this transformation do, but how to inverse or reverse undo this operation. We need a procedure to find it. A straightforward way is by using the definition. What means inverse? Let me assume the inverse of A is B. It has 4 elements, A, B, C, D. In here, A, B, C, D. What I need is A times this B equal to identical. So I got 4 equations. Position by position, the first position here, multiply here, should get 1. And the second position, the first row, and the second column, that's 1, B plus D should get 0. The third position, 0 here. The last one, the second row, the second column, 2C plus 3D equal 1. Well, you can solve this equation easier by elimination. And then we can find this inverse, which is 3, negative 1, negative 2, 1. Well, we can check by multiply the two matrices. Equal 1. That's it. So if you use the definition, how do you find the inverse for A 3 by 3? Well, you see you have 9 elements, then you need to solve 9 equations. That's not, sounds not fun, but we're going to see one at least. Let's look at this one. To find the inverse by definition, you really need the B have this many elements, 9 elements. A is what you know, multiply equals the identical matrix. You can write the identical matrix as B1, the B, this equal E1 is this, the first column, E2, the second column, E3, the third column. If you look column by column, each column you can get 3 equations. That's why you got 9 altogether. Let's just do one to see what do we get. That's my matrix A. You remember this is a projection. We started the last lesson. Question is simple. Use definition. Please try to find the inverse of this matrix. Well, use definition. At least let me get 1 of them. Don't say 3. So assume the B matrix equals B11. Let me just make it easy. X, Y, Z. Don't want to matter this much. Just say this is X, this is Y, Z. I don't care about the rest. And then multiply A times this. See the first 3 rows, multiply the first column. We're supposed to get the first column of the identical, which is 1, 0, 0. As we see here, we should get this one when you multiply this to the matrix. So if we do this, we're going to find the interesting thing. We find these equations. See, the 1/3 is on the front anyway, so 1/3 for here. 2x, that's 2x, 1y, the first row, and the negative 1z, we should get the 1. Because 1/3 of this equal 1, you multiply 3, you get a 3 here. That's the first element here. So the equals 1, 0, 0. Because you have 1/3, that's why you get a 3. The second, 1 times x, 2 times y, 1 times z, what you get is 0. That's the second equation. The third one, negative 1x, 1y, 2z equals 0. Well, we got a very nice 3x3 system equations. So we're supposed to solve that. Let's see what we can do. That's a kind of repeated the procedure to use definition to solve the inverse. If I add the first to the third, what I get? Add the 1 to 3. What I get is 2x minus x is 1x. Y plus y is 2y. Negative z plus 2z is going to be z. 3 plus 0 is 3. Well, I got the fourth equation, which is x plus 2y plus z equals 3. Now you compare to the second equation. X plus 2y plus z equals 0. Then if you let the 4 minus 2, the left are the same, you get the 0 equals 3. No way. That I call it a contradiction. So what? Contradiction means you have no solution. If you don't have any solution, means you really don't have an inverse in this case. So we just find, oh, some matrices just do not have inverse. That's not quite new. Does all number have a reciprocal? Yes or no? The answer is no. If fxa equals 0, you don't have the reciprocal. So the same, not all matrices have inverse matrix. That's nothing new. But if you look in the geometry, you're going to find why. The matrix we checked a moment ago is the projection matrix to the plane z equal y minus x. If this is a projection, you bet it's not going to be one-to-one. Why? You know you can have different vector x1, x2. If they are lined up, you can project them with the same shadow. So clearly, projection is not one-to-one. Just like people could have different looking, but if their shadow is the same, does not mean that people need to be the same. So since it's not a one-to-one, you are not going to inverse it. Just like a function, if it's not a one-to-one, you don't have an inverse. That's why the inverse matrix does not exist. So what do we call it? If the inverse does not exist, we just call it a singular matrix. If the inverse exists, we call it non-singular. That's the two concepts you're going to remember. With this concept, back to the first example, you remember I have this A multiply B, none of them 0, but you multiply it equals 0. You bet these two are singular matrix. None of them have inverse. So A times B equals 0. They are not 0 itself, but they must be singular. Why? Let me show you. Assume if A inverse did exist. So what's wrong with that? Now you can easily get it wrong. You multiply the A inverse on both sides, and this associative A inverse times A equal I. Anything times 0 is 0. And then you get this I times B equals 0. And I times anything equal itself. Then you have the B equals 0, which is not true. B is right here. It's not 0. 0 means all zeros. The same, if the B inverse exists, you get something wrong about the A. So none of them have inverse, then both of them are singular. Well, we learned how to use the inverse matrix to represent the inverse transformation. In the few examples we considered, we found some matrix have inverse, some does not have. Those who has the inverse, we call it non-singular. The matrix has no inverse, we call it singular. Now the question is, we cannot just calculate, wait until we could not find the solution, then we claim the matrix is singular. The easy way is use another concept called the determinant. The determinant looks pretty much like a matrix from the appearance, but there are significant differences. First, I want you to pay attention. A matrix, we use a bracket, put a table of numbers inside. A determinant, we use two straight lines to put the table of number. Most important, the determinant is a scalar. That means your result is 3, 4, 5. You cannot let the table 2 by 2 equal 3 in any way, but you can have a determinant A, B, C, D equal 3. You just need to realize this difference. Now, how do we calculate the determinant? That's pretty simple. If it's 2 by 2, all we need is this AD, A times D, that's the major diagonal, minus BC, minus the minor diagonal. That's called the major diagonal. And this is minor. And subtract. So look at an example. If I need to multiply, calculate this determinant, so I write it down this way. Negative 2, 5, 3, 1/2 equals negative 2 times 1/2 minus 3 times 5. That will be negative 1 minus 15 equal negative 16. That's a number. But you never say this A equals 16. A never equals 16 or 17 or any number. A only can equal A. That's a table. But the determinant of A is negative 16.